Hey, what's up, Chem peeps? What in the heck are we gonna do in this vid? We're gonna describe the electron configuration of an atom using photoelectron spectroscopy data, also known as PES. Alright, let's break it down. Two big things we're gonna do. 1. Interpret photoelectron spectroscopy data to identify an element. 2. Relate the photoelectron spectrum of an element to its electron configuration. Alright, so in chemistry, we use spectroscopy in a number of ways to detect what type and or what amount of a chemical substance might be in a chemical sample. At this point, you want to be comfortable with things like mass spectroscopy, which is used to determine the average atomic mass of an element. We also use colorimeters, spectrophotometers, to determine the concentrations of colored species in solution. So lots of different types of spectroscopy. In this vid, we are focused on photoelectron spectroscopy, also known as PES. And in this type of spectroscopy, we can detect what substance we have by measuring the amount of energy needed to remove electrons. And as you take a look at your screen, we've got this generalized equation to represent some neutral atom that when you shoot a photon of energy at it, it's going to eject one of those electrons and form an ion. So recognize that energy is needed to remove the electron, and we call that energy the ionization energy. And when the electron is removed, we say that the species has been ionized, and the energy needed to do that is the ionization energy, abbreviated IE. And then in this type of spectroscopy, we are just looking at measuring the amount of energy required to remove those electrons in order to identify the element that it is that we're working with, because each element has its own unique electron configuration. Alright, to help you understand this, I'm going to build two atoms, an atom of fluorine and an atom of chlorine. First, I'm going to build some fluorine. 1s, 2, 2s, 2, 2p, 1, 2, 3, 4, 5. Fluorine, all of its orbital glory. Now let's do the same thing with chlorine. 1s, 2. 2s, 2, 2p, 1, 2, 3, 4, 5, 6, 3s, 2, 3p, 1, 2, 3, 4, 5. Alright, so take a moment and observe the two electron clouds, the arrangement of the electrons within the different energy sublevels of these two different atoms, fluorine and chlorine. Observe also the orbital notation of the electron configurations for each of these neutral atoms. I'm also going to put on your screen the Bohr model of these atoms. And the big thing to think about with photoelectron spectroscopy, how tightly held are each of those electrons? The more tightly held they are, the more energy is going to be required to remove those electrons. And the less tightly held they are, the less energy is going to be required to remove those electrons. So let's go back to fluorine. We've got two main energy levels. Let's think about the effective nuclear charge on each of these electrons. In the first main energy level, the two electrons that we find there are closest to fluorine's 9 protons in the nucleus, and they effectively feel a core charge of +9. On the other hand, the electrons in the second main energy level are shielded from fluorine's 9 protons by those two electrons in the first main energy level. And we say they're held with an effective core charge of +7, due to the shielding of the two electrons in the first main energy level. Now let's take a look at chlorine. Chlorine has way more protons than fluorine does. It has 17, and so its two electrons in its first main energy level feel an effective pull of +17, because there's no electrons in between the nucleus and that first main energy level. The electrons in its second main energy level feel an effective pull of +15. They are again shielded by the electrons in the first main energy level. However, chlorine's electrons in its second main energy level are held more tightly with a stronger effective nuclear pull because chlorine has more protons in its nucleus. The electrons in chlorine's third main energy level feel an effective pull of only +7 because its third level electrons are shielded by the electrons in the second main energy level and in the first. Additionally, I want you to think about the S-type sublevel versus the P-type sublevel. Notice that the S or spherical orbital is orbital to penetrate the nuclear region more effectively than the P-shaped orbitals. And so the electrons in s-shaped orbitals are held more tightly, more strongly, than the electrons in the p orbitals within the same main energy level. And those things are really what you want to think about as you think about photoelectron spectroscopy and how much energy is required to remove electrons from the different main energy levels and sublevels within an atom. And in photoelectron spectroscopy, the spectra that are generated simply show the relative number of electrons in a given sublevel and how much energy was required to remove those electrons. So when you're trying to interpret and understand what's going on with a given photoelectron spectrum, recognize that the height of the peak indicates the relative number of electrons, and it's often helpful to use electron configurations to help you interpret those peaks. And also recognize that the position of the peak indicates the relative amount of energy required to remove the electron. Again, I want you to come back to these atoms of fluorine and chlorine and the corresponding photoelectron spectrum for each of the elements. Notice that in fluorine, the 1s and 2s peaks are the same height, because they contain the same number of electrons. However, also notice, as in chlorine, the 2p peak is 3 times as tall as the 2s peak, because it contains 3 times the number of electrons. Let's think about the relative position of these peaks. Notice that in the fluorine atom, the 1s electrons require more energy to be removed than the 2s electrons or the 2p electrons, because those 1s electrons feel a greater effective core charge than the 2s or 2p electrons. Alright, and that pretty much does it for this vid. Check out those guided practice problems to see how you're going to have to work with photoelectron spectra on the test. Have a fantastic day.